In this video, we're going to take a look at some common insulated materials that are used in package design, give some examples, and explain how they work. The first material we'll talk about is nylon insulation. This is a very low-level barrier of insulation material, usually used in bags for short transport, if you're carrying something to or from a clinic or home from a hospital or something of that nature. The nylon itself isn't much of a insulating material, as it is a rugged, durable outer container. What does provide the insulation is the layer of polyethylene in between. If we were to go up the line in terms of what would be the next best layer of protection or insulation for materials used in packaging, a common material would be expanded polypropylene. It's usually formed in a mold in the shape of a container, and by trapping air inside between the beads and inside the beads, it provides a layer of protection. We measure materials insulation by its resistance to heat flow, or R value. EPP has an R value of about 3.5 for every 3 centimeters in thickness of material, slightly less than that of EPS. So the benefit of using expanded polypropylene, or EPP as it's called, over that of nylon is obviously it has greater insulation value, but it's also much more durable. Because it's molded into a tub, it has a stronger bond between the beads, makes it less brittle than, let's say, EPS. It's cleanable, it has greater reusability, and it's recyclable. Very similar to expanded polypropylene is expanded polystyrene, or EPS. This is by far the most common insulation material used for packaging drug products. It's very common and can be molded into many, many different shapes. Again, like expanded polypropylene, the air is trapped in the beads that are fused together, thus providing the insulation. Air naturally has a low thermal conductivity, as we've learned in another video, and the microscopic gaps in the EPS hold the air and create the insulation capabilities of the package. EPS, like EPP, has an R value, or resistance to heat flow, around 4 for every 3 centimeters. EPS, like EPP, has its benefits. It's a pretty good insulator, and compared to other materials, it's relatively inexpensive too. It's very flexible in that it can be molded into nearly countless shapes and sizes. And, best of all, and contrary to popular belief, EPS is very recyclable. So far we've looked at solid materials like expanded polystyrene, expanded polypropylene, and polyester nylon. Now we're going to take a look at a material called airliner. Airliner is an insulated lining material that is placed into a corrugate box. Its metallized laminated film is inflated and produces a low conductivity rate, thus inhibiting heat flow. The benefits of using an airliner container are that it ships flat. It's inflated by the user, so it takes up very little storage space and very little room. Also, after it's inflated, it's primarily made up of air, which is very lightweight, so it's great for shipping small packages with very low weight or volume. It's also reusable, although it's slightly more expensive than a solid container made of expanded polystyrene. So getting back to solid materials, we'll next take a look at rigid polyurethane. The trapped freon gas in PUR has a much lower thermal conductivity than air, and the lower the thermal conductivity, the better the insulation. PUR, as a result, has an R value of about 7 for every 3 centimeters in thickness of material. That's about twice that of EPP, EPS, or even airliner. Aside from being a better insulator than EPP or EPS or nylon or airline, what are some of the other benefits of PUR? Well, for one thing, it's extremely durable and it's reusable. It's very rigid once it's formed into a mold and can be injected into a hollow outer shell, making it even more durable. The tooling costs are moderate, and the expense is a little bit more than EPS or PUR. And in some instances, it's pretty difficult to recycle. So those are all considerations to think about when you're choosing an insulation material like PUR. This brings us to the last common insulated material used in temperature-sensitive packaging, VIP, or vacuum insulated panels. Now, this technology is quite different than the other technologies we've looked at to this point. They're made from nanoporous silica that is encased in a barrier film material, normally a metallized material. It's formed under vacuum, and the silica particles are such size, of common size, about 500 microns each, that allow for very high pack density. So the material, while it's very dense, removes nearly all of the air, thus providing a great barrier for heat. Heat transfer through a vacuum is very difficult, and since we're dealing with vacuum panel insulation, well, you might guess that the heat transfer through this material would take a long time. Well, your guess would be right. The high density of the material and the minuscule air spaces between them prevent heat from transferring through the material. The silica itself has an extremely low thermal conductivity, and as we've learned, the lower the thermal conductivity, the better the insulation. Just how good is VIP insulation? Well, in the world of preventing heat transfer, VIP is champ. It produces a very high R value, about 40 for every 3 centimeters. That's like 13 times that of EPS, or 5.5 times that of PUR. Well, an additional benefit to having VIP panel as an insulation is that it's very, very lightweight. It's also very recyclable, since it's made of silica. But, as you might guess, with benefits, there are drawbacks. The drawback for VIP panel is you're paying for that superior insulation. VIP costs about 10 times that of EPS. And you can't mold it into shapes like you can PUR or EPS or EPP. It comes only in flat panels. It's not nearly as readily available as EPS or PUR. And finally, if the exterior barrier film is punctured, you lose the vacuum. And when you lose the vacuum, you lose your insulation capabilities. Now that we've had a good look at some common insulated materials, what about the temperature stabilizers? Those things inside the package that are intended to keep our product at a desired temperature. Now, these have many different names. They're called refrigerants, they're called gel packs, the terms of wet ice are used, water-based gel packs, phase change gel packs. Although they have different names, they all have one common goal: to keep the product within a specific temperature range. Now, the most common material used as a refrigerant, either refrigerated or frozen, is water. Why do we use water as a refrigerant? Well, there are several reasons. For one, water has a very high capacity for latent heat. Second, it phases at a pretty good temperature, 0 degrees C. It's abundant. It's everywhere. And it's cheap. Other refrigerant materials we have to buy. Water? Well, we don't have to look far to find water. Well, one of the drawbacks of using frozen water as a refrigerant is it can have a tendency to freeze product. And if you have a product that's freeze sensitive, getting it to its phase change temperature with the surrounding frozen water or gel packs can be a potential problem. So what do? There are other materials that are available called advanced phase change materials, or PCMs. Now, phase change materials, or PCMs, are made of, any number of ingredients, from paraffins to eutectic salts. But the latest generation of phase change materials are made from renewable, recyclable, and sustainable animal fat and vegetable fat. They can be constructed in such a way as to dial in their temperature. So instead of material phasing at 0 degrees C, like water, we can shift the phase change point anywhere from minus 25 to plus 30, even higher. Well, we've looked at some options for packaging and for refrigerant, but how do you know which one to use? What's going to make the optimal package? Well, there are other considerations. For instance, how durable does your package have to be? What are the economics? What can you afford? What can you not afford? How far is the package to have to travel in distribution? Do you want to use it one time, or do you want to make it reusable? All of these elements need to be considered when designing a good and efficient insulated packaging system.